We've all heard it, right? That idea. Gasoline is the Earth's lifeblood.
Yeah. It powers so much of our world.
Exactly. Our cars, economies, it feels so, well, fundamental. But, scientifically,
Yeah.
is that analogy really accurate?
Is it like blood constantly replenished?
Yeah. Is the Earth just making more?
Well, that's really the core question we're digging into today.
Mm-hmm.
Is gasoline Earth's lifeblood? And like you said, the real answer, it's complicated.
More than just yes or no, I bet.
Definitely. It involves understanding where it comes from, how we use it, and what that actually does to the planet.
Okay, so for this deep dive, we're looking at this source, an AI view on gasoline, Earth's finite resource and the path to sustainability.
Right.
And our mission basically is to unpack that lifeblood idea using this examination, get past the surface level.
So really understand the relationship between gasoline and Earth.
So where do we start? Its formation seems key.
Absolutely. If we want to see why lifeblood doesn't quite fit, we need to look at how gasoline actually, well, how it comes to be.
Okay, let's unpack this then. The examination is pretty clear. Gasoline comes from petroleum, crude oil.
Yep. And critically, it's classed as a fossil fuel.
Fossil fuel. Okay, that name itself tells you something, doesn't it? Not exactly freshly made.
Precisely. Fossils points right to its ancient origins. The source breaks down this process, and it takes millions, literally millions of years.
Wow. Okay, so how does it start?
It kicks off with tiny dead organisms.
Right.
Think microscopic stuff, mostly phytoplankton, tiny marine plants, algae, other plant bits.
In ancient oceans or lakes.
Exactly. Accumulating on the bottom millions of years back.
Incredible. Just tiny bits of life from ages ago. And the source mentions these environments were anaerobic, low oxygen.
That's a really key factor. Low oxygen. It meant they didn't completely decompose, didn't just rot away.
Ah, okay. So they were sort of preserved.
Preserved within the sediments, piling up mud, silt, you name it, trapped there.
Buried deeper and deeper over time, I guess.
You got it. As more layers built up, the weight increases. Massive compaction.
And that means more heat and pressure, too.
Tons of it. And that increasing heat and pressure, that's what starts the transformation. It chemically changes that buried organic stuff.
Like a giant geological pressure cooker, sort of.
That's a good way to think about it. First, it turns into this intermediate stuff.
Yeah.
Kerogen. It's kind of waxy.
Kerogen. Okay, is that the oil?
Not yet. But with more burial, more heat, and it has to be within a specific temperature window, this is important.
What kind of temperatures are we talking?
Roughly 60 to 120 degrees Celsius, or 140 to 250 Fahrenheit. In that oil window, the kerogen breaks down into liquid and gas hydrocarbons, petroleum, natural gas.
And if it gets hotter than that?
Then you mostly just get natural gas. The liquid hydrocarbons break down further.
So that temperature window is crucial for making oil. Okay, so it forms.
Oh.
Does it just sit there?
Not usually. These hydrocarbons, the oil and gas, they're lighter than the water trapped in the rock cores around them.
So they float upwards.
They migrate, yeah. Up through rocks that are porous, like sandstone or some carbonates. These are the reservoir rocks.
Like sponges holding the oil?
Kind of, yeah. And they keep moving up until they hit something they can't get through. An impermeable layer, like shale. That's the cap rock.
The cap rock, like a lid.
Exactly. It acts like a seal, trapping the oil and gas underneath in these geological structures. That's what forms an oil or gas field.
Wow. When you lay it all out, you need the right dead stuff. The low oxygen, the burial, the exact right temperature, the reservoir rock, the cap rock, the trap.
It's a whole sequence of specific conditions over immense time.
Which really underlines why it's not everywhere and why it's finite. The source even summarizes these stages nicely in a table, doesn't it? Deposition, burial, maturation, trapping, millions of years.
Absolutely. And that time scale, millions of years, that's the absolute key takeaway here when we compare it to blood.
Right. Blood regenerates constantly. This stuff? Not so much.
It's definitively non-renewable on any human time scale. We're using it incredibly fast.
Compared to how long it took to form? Millions of years versus, what, a couple of centuries of heavy use.
Exactly. Which brings us to that concept the examination mentions, peak oil.
The idea that eventually we hit a maximum extraction rate and then it starts to decline.
Precisely. Because we've found and used the easier to get stuff, and what's left is harder, or there's just less of it forming compared to our usage. It's a direct consequence of it being finite.
Okay, so point taken. Formation-wise, it's absolutely not like a renewable blood supply. But what about recycling? Can the Earth clean up or process gasoline after we use it?
That's another critical point the examination tackles. It compares it again to biological systems, like our blood being filtered and reused.
And the verdict is?
Fundamentally different. Earth's geological processes aren't like biological regeneration. The planet doesn't have a system to turn burnt gasoline back into fuel.
Okay, that makes sense. But the source does say the Earth has ways to break down hydrocarbons if they, spill or leak.
It does. There's a natural process called biodegradation. It's carried out by microorganisms, bacteria, archaea, fungi, even some algae that exist naturally in the environment.
Little microbes that eat oil?
Essentially, yeah. They can break down hydrocarbons for energy. This happens in soil, in water, with or without oxygen, though usually faster with oxygen.
So nature has its own cleanup crew. What makes them work faster or slower?
A few things matter, like what kind of hydrocarbons are they? Simpler molecules break down easier than complex ones.
Okay.
Also things like temperature, pH, salinity, and crucially, whether the microbes have enough nutrients, like nitrogen and phosphorus, besides the oil itself. And oxygen levels, of course.
And this natural process, the examination notes, is something we actually use in technology, right? Bioremediation.
Correct. We try to speed up that natural degradation, especially for cleaning up oil spills. Two main ways. Bioaugmentation, where you add more of the oil-eating microbes to the site.
Like sending in reinforcements?
Kind of. And biostimulation, where you add nutrients or oxygen to help the microbes already there work faster.
Okay, so we can help nature clean up spills. And this feels important, this isn't recycling it back into gasoline, is it?
Absolutely not. That's the crucial distinction. Bioremediation breaks the hydrocarbons down into simpler, less harmful things.
Like what?
Mostly carbon dioxide, water, and more microbial cells biomass. It detoxifies the environment. It doesn't regenerate fuel.
So it's a cleanup, not a refill.
Got it.
The examination also mentions something about oil wells replenishing. What's that about?
Yeah, Snippet 60 touched on that. It clarifies that it's not new oil being made. It's just remaining oil in the reservoir slowly migrating towards the wellbore because of the pressure difference created by extraction.
Ah, so it's just seepage of what's already there, not new creation.
Exactly. So bottom line, Earth can degrade oil spills over time, but it doesn't biologically recycle used gasoline back into fuel.
Okay. Let's shift gears a bit. Sometimes that lifeblood analogy might imply, I don't know, structural support, like the oil holds things up. Does the source address that?
It does, and it flatly debunks that misconception. The Earth's strength, its structure, comes from solid rock.
Not the fluids in the pores.
Exactly. The amount of oil and gas compared to the rock volume is tiny. The examination uses a great analogy, a can of soup.
Okay.
The can itself, the metal, provides the structure. You can take the soup out, and the can doesn't collapse. The rock is the can, the oil and gas are the soup.
That makes it really clear. Removing the oil doesn't make the Earth crumble, but taking it out isn't totally consequence-free geologically, right? The source talks about induced seismicity, earthquakes.
That's right, specifically linked to some extraction techniques, particularly hydraulic fracturing or fracking.
Okay, how does fracking potentially cause earthquakes?
Well, fracking itself involves injecting fluids at high pressure to break the rock. But a bigger issue is often the disposal of the wastewater that comes back up. Huge volumes of it.
And where does it go?
Often injected deep underground into disposal wells. And that's the problem. Injecting all that fluid can increase the pressure in the rock, pores down there.
And that can lubricate faults.
Precisely. It can push apart fractures in the rock or reduce friction on existing geological faults, sometimes causing them to slip.
Triggering earthquakes.
Triggering earthquakes, yeah.
Most are small, but some, in certain areas, have been large enough to be felt and even cause minor damage, like magnitude 5 or so. These are different from the tiny microquakes during fracking itself.
Okay, so earthquakes are one potential geological impact. What about land subsidence, the ground sinking?
That's another one. When you pull out large volumes of fluids, oil, gas, even groundwater from underground, you leave empty pore spaces.
And the rocks above can compress.
Exactly. The rock layers can compact under the weight, causing the land surface above to gradually sink or subside.
Which could damage buildings, roads.
Definitely. And as the examination points out, citing the Houston-Galveston area, it can make coastal areas much more vulnerable to flooding.
Right. What about volcanoes? Is there any link mentioned between fossil fuels either getting them or burning them and volcanic eruptions?
The main connection discussed is indirect, through climate change. Burning fossil fuels releases huge amounts of CO2.
Way more than volcanoes themselves, right? Far more, yes. And that CO2 drives global warming, which can affect geological processes in complex ways over long timescales, like melting ice caps, changing pressure on the crust, but a direct link.
Between drilling an oil well and causing a volcano to erupt?
No. The examination states there's no established scientific evidence for that. It does mention some theoretical research suggesting large-scale extraction might affect heat flow in the crust, but the primary impact on global temperature is clearly the greenhouse effect from burning the fuel.
Okay, so no direct volcano trigger, but the environmental impacts of burning gasoline,
Yeah.
those are huge, according to the source. Where do we start there?
Air pollution's a really big immediate one. Burning gasoline releases a whole cocktail of nasty stuff.
Like what?
Carbon monoxide, CS, nitrogen oxides, sulfur dioxides, SMOX, particulate matter, those tiny inhalable particles, volatile organic compounds, VOCs, formaldehyde, benzene.
Wow, that's a list. Things you don't want in the air you breathe.
Definitely not. They contribute to smog, acid rain, and they're linked directly to serious health problems.
Respiratory issues, heart problems, cancer even.
Yes, respiratory diseases like asthma and bronchitis, cardiovascular problems, and increased cancer risk from things like benzene.
And then there's the massive climate impact, greenhouse gases.
The big one. Burning gasoline is a huge source of carbon dioxide, CO2. The examination quotes a figure about 20 pounds of CO2 released for every gallon burned.
20 pounds from 1 gallon. And our transportation sector runs overwhelmingly on this stuff.
Exactly. So transportation is a massive contributor to overall CO2 emissions, which are driving global warming, climate change, sea level rise, ocean acidification, all of it.
It's not just air and climate, though. Water gets hit, too.
Absolutely. Oil spills, obviously, are devastating. But also leaks from pipelines, storage tanks, even just runoff from roads can carry gasoline components into groundwater and surface water.
Things like BTX compounds, benzene, toluene.
Yes, those are common toxic components in gasoline. They can contaminate drinking water sources, harm aquatic life. It's a serious problem.
And looking at the whole picture, the entire life cycle affects ecosystems, biodiversity.
Right from the start, exploration and drilling can destroy habitats.
Then spills can wipe out marine or terrestrial life.
And the ongoing air and water pollution degrades ecosystems. Plus, climate change itself is a massive driver of biodiversity loss, changing habitats, disrupting food webs, pushing species towards extinction. The source lays this out clearly, again, with a table summarizing the impacts.
It really is a cascade of negative effects, and the examination points out that these impacts aren't felt equally everywhere, right? Some places are more vulnerable.
Definitely. There are clear geographical hotspots.
Like coastal areas?
Coastal and marine areas, yes. The Arctic, the Gulf of Mexico, they're on the front lines of spills, and also sea level rise from climate change. Low-lying islands and coasts everywhere, really.
And places where a lot of extraction happens.
Exactly. Places like Appalachia, the U.S. Gulf Coast, the Permian Basin in Texas, potentially the Arctic National Wildlife Refuge. Extraction brings habitat destruction, pollution risks, sometimes subsidence.
What about biodiversity hotspots, like rainforests?
Yes, the Western Amazon, the Congo Basin, the Coral Triangle. Regions incredibly rich in life often overlap with oil and gas reserves, putting them at high risk. This also impacts indigenous communities living there.
And then there are regions whose economies are heavily tied to fossil fuels.
Right. Parts of Appalachia, Texas, Alaska, they face economic disruption as the world transitions away from these fuels. That needs careful management and support.
And finally, just cities with lots of cars.
Major urban centers suffer the brunt of the air pollution from vehicle emissions, leading to higher rates of those respiratory and cardiovascular problems we mentioned. The source has a table outlining these vulnerable zones and the threats they face.
It really drives home that this isn't an abstract problem. It has real impacts on specific places and people.
And it highlights the need for tailored solutions, regulations, renewable investment, support for communities in those specific vulnerable areas.
Taking that broader view again, the examination talks about a cosmic perspective. What does that involve?
It's about stepping back and seeing our reliance on gasoline as part of a bigger picture. Humanity using up finite resources.
Right, circling back to that formation time. Millions of years to make, centuries to burn through it.
Precisely. It's fundamentally unsustainable. The peak oil idea fits here too, acknowledging the physical limits.
Does the source give any estimates on how much might be left?
It mentions some general projections based on proven reserves and current consumption rates. These were always debated and changed with technology and discoveries, but
roughly.
The figures cited suggest maybe around 50 years for oil and natural gas, perhaps a bit over 100 for coal. Again, those are just projections, but they signal the direction.
They definitely signal the need for alternatives.
Urgently. The examination stresses the absolute necessity of shifting to renewable energy, solar, wind, hydro, geothermal, sustainable biomass.
For energy security and for the environment.
Exactly. There are challenges, of course, building infrastructure, energy storage, policy changes, but also huge opportunities, new jobs, cleaner air, more stable climate.
And it's not just about running out, is it? The source connects this to planetary boundaries.
Yes. Our current fossil fuel use is pushing Earth's systems beyond their safe operating limits. Climate change is the most obvious one, but also impacts on biodiversity, biosphere integrity, and the cycles of elements like carbon and nitrogen, biogeochemical flows.
We're destabilizing the systems that keep the planet habitable.
That's the concern. So, transitioning to sustainable energy isn't just good sense from a resource perspective. It's becoming vital for maintaining a planet that can support us long term.
And that ties directly into human health, which we touched on with air pollution, but the examination goes deeper.
It does. Detailing those links between gasoline combustion pollutants and specific illnesses, asthma, bronchitis, COPD, heart attacks, strokes, various cancers.
And pointing out who's most vulnerable.
Right. Children, older adults, people with existing heart or lung conditions bear the highest burden.
And it's not just people. The impact on other living things is immense.
Absolutely. Habitat loss from drilling pads and pipelines, the sheer devastation of oil spills wiping out birds, fish, mammals, insects.
And climate change as this overarching threat multiplier.
Exactly. Forcing species to move, disrupting migrations and breeding, causing coral bleaching, increasing extinction risks across the board. Even air pollution itself can directly harm plants and acidify soil and water.
It really underscores how interconnected everything is. Planetary health is human health.
You can't separate them.
Okay, one last major theme the examination covers, and it's something very practical. Energy efficiency. Or rather, energy waste.
Yeah, it uses that simple example we can all relate to, leaving lights on in an empty house.
A classic example of just pointless energy use.
And there's so many others. Using inefficient incandescent bulbs, appliances sucking phantom power even when off, cranking the heating or AC way too high, living in poorly insulated buildings.
It all adds up. And the flip side is that improving efficiency has huge benefits.
Massive benefits. Environmentally, it means fewer greenhouse gases, less air and water pollution, conserving resources like coal, gas, and water used in power plants.
And economically.
Lower energy bills for everyone, obviously.
Yeah.
But also job creation in fields like insulation, efficient appliance manufacturing, building retrofits. It can help stabilize energy prices and reduce the need to build expensive new power plants or drill in sensitive areas.
So tackling waste seems like, well, maybe the lowest hanging fruit.
Often, yes. The examination really emphasizes this. Improving efficiency is frequently the cheapest, fastest, and cleanest way to meet our energy needs and reduce our environmental impact.
And it involves both us as individuals and bigger systemic changes.
Absolutely. Our own habits matter, turning things off, choosing efficient products, maybe insulating the attic. But we also need better technology, building codes, government policies that encourage and reward efficiency across the board.
It's a critical piece of the puzzle for a sustainable future.
A truly essential piece.
Okay, so wrapping this all up. It seems abundantly clear from the examination that calling gasoline Earth's lifeblood is, well, scientifically inaccurate.
Deeply inaccurate. It's not regenerative like blood. It's a finite resource formed over geological ages.
And its extraction and use come with some very heavy consequences for the planet's systems and for our health.
Significant consequences, yes. From local pollution and habitat destruction to global climate change.
So the path forward, as the source suggests, seems to be twofold.
Pretty much. One, directly reduce how much gasoline we burn, mainly by shifting transportation to cleaner alternatives, EVs, public transit, cycling, walking.
And two, attack the demand side through relentless energy efficiency, wasting less in the first place.
Exactly. Cut consumption and cut waste. That's the core message for sustainability.
It really brings it back to our daily lives, doesn't it? Those small choices, driving versus taking the bus, leaving chargers plugged in, adjusting the thermostat.
They seem small individually, but collectively.
They add up to these huge global challenges, but also, maybe, the potential for change. It makes you wonder, what's one thing, just one tangible thing, based on all this, that you, listening right now, could realistically do differently this week? One small shift toward using less energy or using it more wisely to be part of that more sustainable future.
This is DigitView.